definition of saying that R sub 1 is bigger than R sub 2. We're supposing that R sub 1 is bigger than R sub 2. By definition, R sub 1 minus R sub 2 is positive. That's a definition of greater than that we had earlier in the term. So since that R sub 1 minus R sub 2 equals Q times B, and R sub 1 minus R sub 2 is positive, QB is positive. Since they're equal. And again, I'll prove this next term in algebra, but in number theory, we are taking as known the rules for multiplication by signed numbers. And so if you look at the Q times B there, B is positive up here. B is positive. So if Q were 0, QB, well, this we actually proved 0 times B would be 0. No, QB is positive. And certainly if Q were negative, negative Q times positive B would be negative. So QB would be negative. No, QB is positive. Therefore, Q must be positive. So again, we'll prove next term that 1 is the smallest positive number, smallest positive integer. But since Q is positive, it means it's bigger than 0. It means it has to be at least 1. Q is positive. This is meant to be a colon. So since Q is positive, it has to be at least 1. That's the smallest positive number. If it were less than 1, it would be 0 and it wouldn't be positive anymore. If it were less than that, it would be negative and it wouldn't be positive. So if Q is positive, Q has to be greater than or equal to 1. And we showed earlier in the term, the beginning of the term, that if you multiply both sides of an inequality, so this is weak inequality because it's not strict inequality, it admits the possibility of equality. Nevertheless, we showed that you can multiply both sides of an inequality, either way, greater than or equal to, by the same positive number. And again, up here, B is positive. So multiplying both sides by, and again, the way you would read this is not multiplying both sides by B is greater than 0, but multiplying by B, which is greater than or equal to 0. We get what order did I write it in? QB is greater than or equal to, well, 1 times B. And of course, that's QB is greater than or equal to B. Okay, so going back to R sub 1 minus R sub 2 equals QB. This says R sub 1 equals QB plus R sub 2. Add R sub 2 to both sides. And so that is greater than or equal to B plus, well, it's just greater than or equal to B since this cube B is bigger than B, and since R sub 2 is positive, and so we have that term is greater than or equal to B. We just proved that before. It says going back to. So this cube B is bigger than or equal to B, and the R sub 2 from the hypothesis in the beginning, R sub 2 is positive. So that means R sub 1 is bigger than QB, which is greater than or equal to B, plus something that's positive, means R sub 1 is greater than or equal to B, but that contradicts the supposition with the possibility that they're not equal, that R sub 1 is bigger than R sub 2. And so since R sub 1 and R sub 2 can't be different, because if they are, one is bigger than the other. And we saw that assuming that one is bigger than the other leads to a contradiction. R sub 1 equals R sub 2. Which is what we wanted to prove. Okay, so what's the point of this? I mean, aside from the fact that it's true, I want to use it to show uniqueness. So last Thursday, we actually showed that just to review, we showed that any positive integer m can be written as something like, say, a sub n b to the nth plus some other coefficient b to the 1 lower power n minus 1. So its coefficient, I'm just calling a sub n minus 1, and so on, down to b to the 2, so its coefficient would be a to the 2 plus b to the 1, so its coefficient would be a sub 1, plus b to the 1 lower power, which is 0, so it's just 1 plus some coefficient of 1, a sub 0, where the base b is greater than 1, the base or the radix. And all the a sub n's are a sub I less than b for I equals so these could be less than or equal to b, and 0 is strictly less than a sub n, which is less than b. And so, for instance, 2, 3, 4, which means base 10, is 2 times 10 to the 2 plus 3 times 10 to the 1 plus 4. And if we take 2, 3, 4 in, say, base 6, that would mean 2 times, instead of base 10 to the second, it would be times base 6 to the second plus 3 times, instead of the base 10 to the first, it's base 6 to the first plus 4. And then we saw we could the very proof that we could do this also showed us how to actually do it. So to convert from base 10 to another base repeatedly, divide the given base 10 number. A base 10 number. No, it's the number. It's written in base 10. It's not that it's a base 10 number. The number is the number. But anyway, I guess it's customary to say the base 10 number, the number in base 10 by the new base, the base that you're converting it to, saving the remainders, keeping track of the remainders, and listing the digits of the number in the new base. In the reverse order, the opposite order, the way I did it, I worked downwards, so the digits were going from bottom to top. The digits of the new number, of the number in the new base, in the reverse order of how you computed them. And so we show that you can convert, that you can write any number m as any positive integer m as a sum up here, a sum of multiples of non-negative powers of a number greater than 1, called the base, where each of those coefficients of the powers of b are non-negative integers less than b. And in fact, the first one, the a sub n, would be strictly greater than 0. Otherwise, it wouldn't have that number of digits. You'd have a 0, as we discussed on Thursday. So what we're going to do almost next, but I want to do an example first, then we'll do it. So I'm sure it never even occurred to you, since you learned to count well before school, before you started school, 1, 2, 3, 4. I'm sure it never even occurred to you to wonder whether you can express a number, I don't know, let's say your age, in more than one way, in base 10. I mean, if you're 20 years old, you'd write your age as 20, and probably never thought of, well, can you write it in a different way? And the answer is no, and we'll prove that after we do an example. We'll prove that the representation of a number in a given base, that's what I underlined above, m equals a sub n times b sub n. The underlined statement, that's m written in base b, or in the scale of b. So again, on Thursday, we proved existence, and after this example, we'll prove uniqueness. So let's, convert, say, 254 in base 6 to base 4. Let me just say, you know how in elementary school, I seem to recall that for me it was in the 4th grade, at least mostly, you had to memorize the multiplication tables. So, 4 times 12 is 48. And I don't know, to this day, I'm glad I know the commutative law, because it really cut in half the number of combinations I had to remember. And to this day, if I have to do 7 times 8, I'm actually thinking of 8 times 7, which I remembered was 56. But notice I just said remembered. And indeed, that's what it is. 8 times 7, or if you insist, 7 times 8, is 5, 6, which we read as 56. And again, speaking of reading, as I said on Thursday, if you look at the number I just wrote, that is not 254 base 6. If it's other than in base 10, you have to read the digits. So that number is 254 base 6. I mean, you could say, and sometimes to be clear, like if you're reading a number to someone in base 10, you would say 254, or of course you could say in base 10, 254. But again, you can't read it that way if the base is different from 10. But so 7 times 8 is 56, and that really is a matter of memorizing that the number that 7 times 8 is, when it's written in base 10, is 5, 6. 7 times 8 is a number, however you write it. And so in a different base, it would be written differently. So if you were doing arithmetic in a different base, you would be dealing with the same thing as you did in base 10, where you really had to memorize the multiplication table for individual digits up to 9. So 9 times 8, 9 times 6, 8 times 4, 7 times 2, and so on. You had to memorize those. And then using algorithms, you could extend the multiplication to, a 2-digit number by a 2-digit number, or an m-digit number by an n-digit number. There you would be doing all the arithmetic, just extending it. You'd be doing all the arithmetic in base 10, having memorized the table for base 10. You could do the same thing. And there's nothing sacred about base 10. It'll never change. That's the way numbers are counted. Although other systems of counting have been used. As you know, the binary system is used for computers, but other bases have been used. We presumably get base 60 for minutes and seconds from the Babylonians. And how do you say 80 in French? Quatre-vingts? My pronunciation isn't very good. It's 4 20s. So 20 has been used as a base. What does a gross mean? It means a dozen. 12 has been used as a base. So if you look at arithmetic and numbers linguistically, we can see vestiges of other numeration systems. And whatever base you're using, it would just be a matter of learning the multiplication table, and therefore division as well, the multiplication table in that base. So you could learn, for instance, in base 2, so 2 times 2 is 4. So in base 2, 2 is 1, 0, and because it's 1, 2 plus 0, and 4 is 1, 0, 0. So it's 1 times 2 squared plus 0 times 2 to the first plus 0 times 2 to the second. So, you could learn a whole arithmetic in a different base. Since we're not going to do that, my suggestion is do this, meaning this example. in 2 steps. Since we're more familiar with the decimal system, namely the base 10 system, first convert base 6, the base 6 number, to base 10, then convert that to the new base 4. So let's do both of these because this example will exemplify both of the computational methods that we had Thursday, and then we'll prove uniqueness. So remember, 2, 5, 4, base 6. Sometimes you put it into parentheses. Remember, this is, I called it a code for. So again, you have to read from right to left for a number. So this is 6 to the 0th. This is the number of 6 to the 1st. This is the number of 6 squareds. So the 2 is the number of 6 squared. So it's 2 times 6 squared plus, the plus is up here on what's underlined for M. It has plus signs, plus the 5 is the number of 6 to the 1s, and then again plus the 4 is the, well, it's just 4, it's the number of 6 to the 0ths. So in more familiar decimal form, base 10 form, 6 squared is 36 times 2 is 72, plus 5 times 6. And again, I think of this as 6 times 5, but whichever way it is, thank goodness for the commutative law, is 30 plus 4. So 72, 82, 92, 102 plus 4 is 106. And base 10. Okay. Now change the number 106 to base, what do we want, base 4. Right, so what we did was we took the 106 and just for convenience and working down, because you have space below but not above, and in advance you don't know how many divisions it would take, so you'd have to write 106 down here and then go up and get the answers up. But since you don't know how much space to leave, I'll work down. So we're going to successively divide by 4, get the quotient, and save. We'll make a note of the remainders. So 4 into 10 is 2, and then this makes it 26. So 4 into 26 is 6, remainder 2. All right, equals. And then keep doing this division by 4. 4 into 26 is 6 with a remainder of 2. Keep dividing. 4 into 6 is 1. Remainder equals 2 again. All right, keep dividing by 4. 4 into 1 is 0. As we showed on Thursday, these numbers get smaller and smaller, so eventually this does come to an end with a remainder of 1. So we work upwards. Answer 106. And again, if you don't specify the base, it's understood to be base 10 in base 4 is 1, 2, 2, 2. And again, even though I've said in base 4, for emphasis, I'll put that in. Again, this is going to be the number of 4 to the 0s. This is going to be the number of 4 to the 1s. This is going to be the number of 4 to the 2s. This will be the number of 4 to the 3s. So it means 1 times 4 to the 3rd plus 2 times 4 to the 2nd plus 2 times 4 to the 1st plus 2 times 4 to the 0th. 4 to the 3rd is 4 times 4 is 16 times 4 is 64 plus 4 squared is 16 times, make sure you have a time sign there, times 2 is 32 plus 2 times 4 is 8 plus 2. 64 plus 32 is 96. 8 plus 2 is 10. I'm grouping them using the associative property. So yeah, 96 plus 10, yeah, is 106. Check. Okay. Okay, so on Thursday, we very carefully went through the proof with a repeated use of the division algorithm, and we had a million subscripts. To do it formally, I would go through that again, but instead, let's show an example which is indicative of exactly what we would be doing without using a lot of subscripts. So to avoid subscripts, instead of having an n-digit number, I'm going to say, suppose a positive integer, I used m up here, I believe. Yeah, m. Can be written let's say 1 with 5 digits, and suppose it can be written another way, maybe with 3 digits. So suppose, for instance, by the way, if we have a 5-digit number, what power of the base do we go to? Well, considering that the last digit, as you read from left to right, the last digit has the power of the base as 0. To have 5 digits, you're counting up from 0. So If you were counting up from 1 up to 5, it would be 1, 2, 3, 4, 5. But we're actually starting at the right with 0, and then the next column would be 1. So that's 2 digits. The next column would be the second, would be the third digit. So actually, let's take a look at this. Suppose, and again, I'm doing it for a semi-specific case of 5 digits and 3 digits. I say semi-general because I'm still using whatever the coefficients are. Suppose, for instance, say m can be written in 5 digits as, say, a let me use, I want to use letters at the beginning of the alphabet for coefficients for up here, the underlined A sub. I just want to avoid a lot of subscripts the way I have up here underlined. So instead of using B as the base, I'll use R as the base, R for radix. Let R be the base. So I want to show that the number m can be written in exactly one way for a given base R. So suppose m equals, so again, it's going to be 5 digits. So I'm going to go up to R to the 4th plus B R to the 3rd plus C R to the 2nd plus D R plus E. And let's suppose, again, suppose that equals, what are we up to, F? And again, for a 3-digit number, I'm going to go up to R to the 2nd plus G R, it's after GH plus H. So again, counted, I went up to R to the 2nd, but there were 3 digits there. For the first one, there were 5 digits, but we went up only to R to the 4th because we started with E times R to the 0th, where I'm not going to list all the coefficients, where all the coefficients of the powers of R remember, we showed that on Thursday. We also discussed how if you're writing a number in base 10, all the digits are less than 10. Once you get up to 10, you move it to 10 to the 1st plus 0. So yes, the coefficients of the powers of R are less than R. And the coefficients are the digits of the number. Yeah, so again, those coefficients are the digits of the number, just as we were saying up here, for instance, in this 254, base 6, the 2, the 5, and the 4, here they are the digits of the number. Again, as I mentioned on Thursday, digit etymologically refers to 10, but we're going to use digit as the figures that compose the number in any base. Okay, so all right, so let's write this as AR to the fourth plus BR to the third plus CR to the second plus DR minus FR to the second minus GR. So I've taken all terms with R's in them and put them on the left, and all terms without R, or R to the zero, so without R, I'm going to have on the right. So we have the H here, and we had the E on the left minus E. Okay, so I just separated the terms with the R's on one side and the constants without the R's on the other side. So I'm not going to rewrite this whole thing. So notice that on the left side, since I put all terms with R on the left, all those terms have R's in them. So you could pull, I'm not going to write this, but you could pull out the R and have it as R times, whatever is left in there, which would show that R divides H minus E. Since H and E are not the digits, some of the digits are just, I'll just say are digits. Of this number M up here, they're digits. So remember that as we showed on Thursday and we repeated today, the digits are less than the base. So again, as we just said about 10, base 10, any number base 10 has digits that are all less than 10. And so as we showed on Thursday, the digits are all less than the base, which is R. But we started by proving the lemma that says if over here R divides H minus E, then that can happen only if they're equal. So if you have a bigger number dividing a difference of two numbers that are small, two positive numbers that are smaller than it, then necessarily the two numbers are equal. So that's what we have over here. So up here, we have E on the left and H on the right. We can subtract, and they're equal, so we can subtract them. We can subtract E from the left side. And what it's equal to, H on the right. And that will give us just AR to the fourth. Again, there's a lot of writing here, but notice that no step whatsoever. Last Thursday, it may have looked complicated and you have to follow the subscripts and everything. No step that we're taking transcends elementary algebra. We're taking out a common factor, we're subtracting the same thing from both sides. It's only elementary algebra. So we have AR to the fourth plus, so, don't be overwhelmed by this. It's not mathematically difficult. So for M up here, we have AR to the fourth plus BR to the third plus, this is what's underlined, CR to the second plus DR. And so we've gotten rid of the E. And so we're just left with FR squared plus GR on the right. We got rid of the H. Now, I'm not going to rewrite this, but strictly speaking, what I'm doing now, notice that every term that's left there has an R in it. So using the sort of the reverse of the distributive property, which we call factoring, but it's really the distributive property. Notice that on the left side and on the right side, you could pull out a common factor of R. Do you see that? So it's R times something. And then we proved the cancellation law. In an integral domain, the cancellation law of multiplication says that if you have a non-zero R, and R is non-zero, it's the base, so it's at least one, you can, quote, cancel the common factor on both sides. And when you do that, I mean, you see what we're doing here at this step. So in elementary algebra, okay, you divide both sides by R, which is what I'm doing. But, what is the basis for that? What allows you to do that? What makes it valid? Well, we've built up things that make each step valid based on the actual theory, not just on sort of, well, okay. And by the way, I mean, if you are ever helping someone in elementary algebra, you're not going to be talking about integral domains and the cancellation law and the fact that in an integral domain, you have no proper divisors of zero. No, I mean, you would say if you have two things that are equal, and if you take, say, half of each one, then the results are equal. If you divide in general by R, the results are equal. It's only when you get to higher levels like this that you have to start questioning exactly what's happening. And the reason for that is partly to rationalize it, to make it rational, but it's also partly because when you get to higher levels, and some of you already have in some areas, such as mathematics 4010, if you don't have a solid, firm, rigorous basis on which to reason, it just gets out of hand, and you very quickly kind of like don't really know what you're doing. And all of a sudden, is it from Alice in Wonderland, the expression a house of cards that can just, collapse? And that's what happens. So that's why you actually need this care and rigor. So we get, so it's going to be reduced. We have AR to the third. I'm dividing through by R, which is really the cancellation property. AR to the third from this last equation plus BR to the second plus CR plus D. And on the right, when we get rid of an R, we have, that's not a formal mathematical expression, get rid of the R. We get FR plus G and do it again. Repeat the same strategy. Get all terms with R in them on the left and the terms without R on the right. So we'll have AR to the third plus BR squared plus CR minus, we have R's on the right, minus FR. And then we have, on the right, we have a G. And then we have to subtract the D. And so, again, we see that R, which is a common factor of the right side, of the left side, divides G minus D, and you need parentheses there because it's the whole thing. And same reason as before, all the coefficients, the G and the D, are less than R. If R divides their difference, the lemma says those two numbers have to be the same, so R divides 0. So G has to equal D so that G minus D is 0 and R divides it. Otherwise, R would not divide any number, which would be that difference, G minus D, that's less than R, unless that number is 0. So now, leaving this, leaving the last underlined equation as just AR to the third plus BR to the second plus CR, and we're subtracting D from the left and G from the right, equal to FR. And again, so all those terms have R's. R is different from 0. R is a base, so it's greater than 1, so you can divide by it. Dividing through by R leaves AR to the second plus BR plus C equals F. And then we'll have AR to the second plus BR, same as before. Terms with R on the left, the other terms on the right, F minus C. And so that says R divides F minus C, you need parentheses. And so since R divides two numbers small, the difference between two numbers smaller than it, those two numbers have to be the same. And so we have AR squared plus BR equals 0. taking out a common factor of r. So that will give us, let me write it formally this time. Look at what this says using the properties of an integral domain. So this says from the distributive property r times AR plus B, and I'm going to write this 0. We did this once before, R times 0. And so now you have that R not equal to 0. And so the cancellation law in an integral domain says cancellation law for multiplication. So we have this, where remember A, B, and R are positive. Well, I guess B doesn't have to be positive. So A and B are positive. They're digits, so they have to be non-negative. Let me actually write if AR. So if this term or this term, if either one of those is positive, the other term would have to be negative to add up to 0. So neither AR nor B can be positive. And again, neither is negative because R is at least 1, so it's positive. And A and B can't be negative because they're digits of the number. So neither is negative. So the only way that can happen, if either AR or B is positive, the other would have to be negative to add to give 0, and that can't happen. B is not negative, A is not negative, R is actually strictly positive. So in fact, the only way, since neither A nor B can be negative, that means neither one can be positive because their sum is 0. So neither one of those terms can be negative. Neither can be positive because the other can't be negative, so they both have to be 0. And of course, if AR equals 0, cancellation property, well, not even a cancellation property. In an integral domain, if a product equals 0, one of the factors has to be 0. So since R is not 0, A must be 0. Reason, in an integral domain, if a product is 0, one of the factors is and B is greater than 1. So it's not 0. So A has to be 0. Okay, so look at what we have. We found that the extra coefficients, the coefficients A and B in M, that were coefficients of powers of R that were higher than the powers of R in the other representation on the right side of the equation I just underlined. You have R to the second. So notice that on the left side, where you have terms with higher powers of R, like R to the fourth and R to the third, the A and B, the coefficients have to be 0. So those are essentially wiped out. And what you're left with is that the powers are equal. And furthermore, if you look at what we proved, H equals E. So those were equal. Then we successively, wherever we have it down here, so we have H equals E. Then we successively got G equals D. So there G equals D. And then further down here, we got F equals C. So there's C and F. And so that completes the proof. We proved that if you think you can write M with more terms than another way of writing it, like over here 5 terms and over here 3 terms, no, the extra terms just, they're there with coefficients of 0. In other words, they're not there. And then once they're not there, we found that you were left with just 3 terms on each side, and the coefficients for them had to be the same. So that completes the proof of uniqueness, and unfortunately, it looks as if that will complete our class for today. So what we'll do on Thursday is talk about the number of digits to represent a number. I don't know if you've ever seen something that says, I don't know, some enormous number, 2 to the 50th power would be written and would have a certain number of digits in base 10. How do you find that out? How do they know that? 2 to the 50th would be an enormous number. You're not going to write that out and then start counting the digits. Well, we'll see a very efficient and effective way of doing that on Thursday. And let me remind you, preparatory to that, let's recall something that we had at the beginning of earlier in the term. Recall the greatest integer function with a bracket function. That colon equals the unique integer m such that m is less than or equal to x is strictly less than m plus 1. So, for instance, we had 2.3 in brackets is 2. The greatest integer less than or equal to 2 is 2. The greatest integer less than or equal to -2 is -2. But suppose we take negative 2.3 in brackets, the greatest integer less than or equal to negative 2.3, if you think of this on the number line, is negative 3. So just recall that, and let's leave it at that for now, and I will come back to you and chat with you a little bit if you want. So we will stop broadcasting.
The recording has stopped.
Okay, so yes, the recording has stopped and the lesson has stopped, and